Let me start with something really basic, something that seems simple, but which is actually the root of the whole problem. How far away are the stars? You see, we live here on Earth, and Earth is already pretty far from other planets. If you want to go to Mars, that's interesting. It takes months. If you want to go to the outer planets, that takes years. Neptune, the Voyager spacecraft, took 12 years to get there. That's a long time, right? But here's what's wild. The distance to Neptune is tiny, absolutely tiny compared to the distance to even the nearest star. Let me put this in perspective for you. The nearest star to us, Proxima Centauri, is about 4.25 light years away. Now, what does that mean? Well, light is the fastest thing we know. Light travels at 300,000 kilometers per second. That's incredibly fast. And Proxima Centauri is so far that even light, the fastest thing in the universe, takes 4.25 years to get there. 4.25 years just for light to make the journey. If you think about it in terms of distance, it's roughly 40 trillion kilometers. I want to say that number again because it helps you understand how big this really is. 40 trillion. To give you some perspective, Voyager 2, which is the fastest spacecraft we've ever sent in this direction, traveling as fast as it can, would take over 100,000 years to reach Proxima Centauri. 100,000 years. That's longer than human civilization has existed. And here's the kicker. Proxima Centauri is the nearest star. All the other stars are even farther away. The next nearest ones are light years away. Our galaxy, the Milky Way, is 100,000 light years across. Do you understand what that means? Even at the speed of light, it would take 100,000 years to cross our galaxy. And we're going nowhere near the speed of light, we're nowhere near it. So the first problem is just the sheer brutal distance. But that's not even the real problem. The real problem is energy and physics. Let me think about what it takes to accelerate something to high speed. Suppose you want to take a spaceship, not even necessarily with people in it, just a probe, something relatively small, and you want to get it to another star in a reasonable amount of time. What do you need? Energy, a tremendous amount of energy. Here's where the math gets interesting, and I want you to follow this carefully because this is where the science fiction dreams start to crash into reality. To get a spaceship to go faster, you need to burn fuel. That fuel has mass. And when you burn the fuel, you're trying to accelerate not just the spaceship, but also all that fuel you're carrying. So to accelerate the fuel, you need even more fuel. This is called the rocket equation, and it was figured out a long time ago by a Russian scientist named Tsiolkovsky. The rocket equation says something very uncomfortable. To get to higher and higher speeds, you need exponentially more fuel. Not a little bit more, a lot more, exponentially more. Let's say you want to get a spacecraft to 10% of the speed of light. That's about 30,000 kilometers per second. That's still incredibly slow compared to what you'd need to make interstellar travel practical. But let's use it as an example. The mass ratio, the amount of fuel you need compared to the actual spaceship, has to be between 1,000 and 1,000,000 times the mass of the spaceship itself. 1,000 to 1,000,000 times. Think about what that means. If you want a spaceship with a crew of, say, 100 people, or even just a probe that weighs 1,000 kilograms, you need to start with 1,000,000 kilograms of fuel just to accelerate. But wait, it gets worse, because you can't just accelerate halfway and coast. You also need to decelerate when you get there. Otherwise, you'll just zip past the star and go flying into the cosmic void. So you need that same enormous amount of fuel to slow down. Now you need 2,000,000 kilograms of fuel. Or maybe you want to swing around and come back, then you need even more. And remember, I'm only talking about getting to 10% of the speed of light. That's still 2,000 years to get to Alpha Centauri, most of a human lifetime gone on a single mission. If you want to go any faster, you need exponentially more fuel. Now you might say, well, what about these exotic propulsion systems, nuclear fusion rockets, antimatter engines, laser-pushed solar sails? These are interesting ideas, and scientists have thought very seriously about them. Some of them could theoretically work, but they all run into the same basic problem. You still need enormous amounts of energy, and you still have to carry your fuel somehow, and you still have to obey the laws of physics. Let me talk about a few of these ideas and why they don't solve the fundamental problem. There's an idea called Project Daedalus from the 1970s. This was a serious engineering study of what it would take to send a probe to Alpha Centauri using a fusion rocket, essentially using hydrogen fusion bombs to push the spacecraft. And you know what? The scientists working on Project Daedalus were careful and rigorous. They looked at what was actually possible with known physics, and they concluded that you might be able to send a relatively small unmanned probe, we're talking about something weighing less than 1,000 kilograms, to Alpha Centauri in roughly 100 years. 100 years of constant acceleration and coasting. That means no living creature from Earth could make that trip. The astronauts would be born on the spaceship, grow old, have children, and their children might die before ever arriving. Or you could send robots, and the robots would arrive at their destination after 100 years of traveling through empty space with no way to turn around and come back. That's the reality of Project Daedalus, which was supposed to be one of our most optimistic designs. And remember, that requires solving enormous technical problems. You need to contain deuterium and helium-3 fusion reactions in space. You need to protect the spacecraft from the radiation. You need to have engines that can run continuously for 100 years. These are not small problems, and it still takes a century to reach our nearest star. Now, here's something that really bothers me. We haven't even talked about the human problems yet. We've just been talking about the physics and the fuel. But if you actually want to send living human beings on one of these missions, the problems multiply. Think about it. You're in a spacecraft traveling through empty space. There's cosmic radiation all around you, not just the radiation from the sun, but high-energy cosmic rays coming from all over the galaxy. These are extremely energetic particles that can damage your cells, cause cancer, cause genetic mutations, damage your DNA in ways we don't fully understand. Right now, we don't have any good way to shield against cosmic rays. We can't build walls thick enough because they would be too heavy and they wouldn't work anyway. Cosmic rays just pass through. You could use a powerful magnetic field, but that requires enormous amounts of energy, and it's still not clear it would work well enough. The shielding problem alone makes sending humans on long interstellar journeys incredibly difficult. And that's just one problem. You also have the psychological problem. Imagine you're on a spacecraft with the same few hundred people for 50 years, 100 years, maybe longer. You can't go outside. You can't take a walk in nature. You see the same walls, the same people, day after day after day. Some scientists have predicted that the psychological effects would be devastating. People might go mad. There could be violence. There could be mutiny. We've never actually tested what happens to human psychology when isolated for decades or centuries. Then there's the biological problem. Your bones get weaker in weightlessness, your muscles atrophy, your immune system gets confused, your eyes can swell from the fluid shifts in your body. We see these effects in astronauts who spend a year or two in space. Now imagine 100 years. What happens to human biology over that time scale? We don't know. And here's another thing. You need to keep the spacecraft working, all of it, for the entire journey. We're talking about machines that have to function flawlessly for years or decades or centuries. On Earth, when something breaks, you call a repair person. In space, you are the repair person, and if something critical fails, you die. You're stuck on a machine traveling through the cosmic void, and if the life support system breaks down, or the radiation shielding fails, or the propulsion system breaks, you die. Nobody's coming to help you. So now you see what I mean. Even if we solve the physics problems, and I'm not sure we can, the engineering problems are enormous, and the biological and psychological problems might be insurmountable. Let me talk about some other ideas people have proposed and why they don't work as well as the science fiction makes them sound. One of the popular ideas is something called cryosleep, or suspended animation. The idea is that you freeze the astronauts, put them into some kind of hibernation, and they sleep through the whole journey. That way they don't age, they don't suffer from the psychological effects of isolation, they don't get as much cosmic ray damage. It sounds great in the movies, but here's the problem. We've never successfully frozen a mammal and brought it back. We can freeze sperm and eggs for storage, but a whole human being, with all the complexity of the brain, the blood vessels, the organs, this is much harder than it sounds. And even if we solve that problem, which we haven't, you still have the problem of keeping the cryogenic equipment working for decades or centuries. One little malfunction, one power interruption, and everyone wakes up dead. Some people have talked about generation ships, huge spaceships designed to support human life for centuries, with multiple generations being born and dying on the ship until finally great-great-great-grandchildren arrive at a distant star. It's a beautiful idea in principle, but it requires solving almost all the problems at once. You need a completely self-sustaining ecosystem in a spacecraft. You need to grow food. You need to recycle water perfectly. You need to generate power. You need to maintain the entire structure for hundreds of years. You need to keep humans psychologically stable across multiple generations while locked in a metal box. It's theoretically possible, maybe, but the engineering is staggering. Then there are these more exotic ideas that physicists have proposed. Wormholes, for instance. Einstein's theory of general relativity allows for the possibility of wormholes, shortcuts through space-time where you could, in principle, go from one point in the universe to another point very far away. It sounds fantastic, but the problem is that the wormholes we know about from Einstein's equations are not stable. They would collapse instantly. To keep a wormhole open, you would need something called exotic matter, which has negative energy, negative mass. We've never observed exotic matter. We don't know if it exists. And even if it does, you'd probably need a quantity of it roughly equal to the mass of Jupiter. And you'd need to position it just right. This is pure speculation. It's not technology, it's wish thinking. Then there's the warp drive concept, which came from another physicist, Miguel Alcubierre, who showed that Einstein's equations technically allow for a bubble of space-time that travels faster than light. You would compress space-time in front of the spaceship and expand it behind, and the ship would surf on the bubble. Sounds marvelous, doesn't it? But again, this requires exotic matter, and not just a little bit, enormous amounts of it. And we don't know if exotic matter exists, and we don't know if you could make it stable, and we don't know if you could make it do what you want. So again, this is speculation. I want to be honest with you. These ideas are theoretically consistent with Einstein's equations. They don't violate the laws of physics as we understand them, but they require knowledge we don't have and technology we can't even imagine building. They're in the realm of not ruled out by physics, which is very different from actually possible. So, where does that leave us? If we can't go faster than the speed of light, and Einstein's relativity says we can't, then we're stuck with relatively slow speeds. Even getting to 10% of the speed of light requires technology we don't have and energy sources we can't access. And even if we did get there, it would take us over 200 years just to reach the nearest star. And when I really think about it from a practical standpoint, I have to ask, why would anyone bother? Why would you send humans on a 100-year or 1,000-year mission to reach another star? There's no economic reason. There's no practical reason. You can't bring anything back. You can't communicate with Earth. The radio signals take years to get there and back. By the time you send a message and get a reply, decades might have passed. If I were an advanced alien civilization and I wanted to explore the galaxy, I wouldn't send living creatures on these journeys. I'd send robots. Robots can be put into hibernation, or they can be designed to survive radiation. They don't need food or air or psychological support. They don't care if it takes 1,000 years to reach somewhere. And once they get there, they can send back information, maybe build more robots and spread through the galaxy. Robots are orders of magnitude easier than living beings for interstellar travel. And this actually helps explain something that has puzzled scientists for a long time. It's called the Fermi paradox. The universe is huge. There are billions of galaxies, each with billions of stars. The laws of physics that allowed life to evolve on Earth are the same laws that apply everywhere. So statistically, there should be plenty of life out there. Intelligent life, alien civilizations, maybe even civilizations far more advanced than us. And yet we don't see any evidence of them visiting Earth. We don't see signs of them colonizing the galaxy. The universe seems silent. Why? One explanation is simple. Interstellar travel is really hard. It's so hard that even advanced civilizations might not bother with it. They might stay near their home star system. Or maybe they send out robot probes, but those probes don't come to Earth. Maybe they go somewhere else. The point is, the difficulty of interstellar travel might explain why, despite the apparent vastness and age of the universe, we haven't been visited by anyone. Now, I don't want to be completely discouraging. There are some things we could potentially do. We could send unmanned probes, small ones. Right now, there's a project called Breakthrough Starshot that proposes to use laser beams to push tiny spacecraft, we're talking spacecraft weighing just a few grams, to 20% the speed of light. They might be able to reach Proxima Centauri in about 20 years. That's an interesting idea, and it doesn't violate physics. But you're not going to get humans on a spacecraft that weighs a few grams, and those tiny probes would be fragile. A collision with even a speck of dust at that speed could destroy them. The plan is to send thousands of probes, hoping that at least a few make it. Or maybe in some very distant future, we develop new physics that we don't understand now. Maybe we'll discover something about quantum mechanics or general relativity that opens up possibilities we can't imagine. Science is full of surprises, but we shouldn't count on surprises. We should be honest about what we know. Here's what we actually know. First, the distances between stars are enormous, so enormous that even light takes years to travel between them. Second, accelerating anything to high speeds requires exponentially more energy and fuel. Third, there is a speed limit, the speed of light, that appears to be absolute and unbreakable. Fourth, Keeping humans alive for decades or centuries in space requires solving problems we haven't solved and might not be able to solve. And fifth, the most exotic ideas, wormholes, warp drives, shortcuts through space, require physics we don't understand and matter we've never observed. So when someone tries to tell you that interstellar travel is just around the corner, or that we'll definitely be sending humans to other stars in the next few hundred years, I want you to think about these facts. Be skeptical. Ask them the hard questions. How fast will the spacecraft go? How much fuel is required? How will the crew be protected from radiation? How will they survive psychologically? And when they can't answer these questions with actual numbers, when they fall back on vague ideas about advanced technology in the future, you'll know they're not being very careful about the physics. Now, I've been talking a lot about problems, and I realize that might sound pessimistic, but I want to be clear about something. I'm not saying interstellar travel is impossible. I'm saying it's incredibly difficult, far more difficult than most people realize. It's not something we're going to do casually, the way we might take a flight across the country. It requires confronting fundamental limits in physics and engineering. But here's what I think is interesting and what I want to leave you with. The difficulty of interstellar travel teaches us something profound about the universe. It teaches us that the universe is vaster and stranger than our intuitions tell us. It teaches us that the laws of physics are very real and very limiting. And it teaches us that we should be humble about our place in the cosmos. We're stuck here on Earth, on this little planet. The stars are beautiful to look at, but they're not our destination. And maybe that's okay. Maybe there's plenty to explore and understand right here. The real value of thinking carefully about interstellar travel isn't in building spaceships. It's in learning to think clearly about physics, about energy, about the constraints that nature puts on what's possible. And that kind of clear thinking, that's something that's always valuable. That's the real lesson here.